Hello everybody. In our series of lectures on basic electronics, let us move on to the next. You might recall in the previous lecture we discussed about the comparators, operational amplifier used as a comparator. We discussed about different application circuits like the window comparator, where you have the op amp sensitive enough to detect the transition at different levels. For example, there is a low output between limits is one variation of the comparator, and the other one is the output will become high whenever the input voltage is between the two limits. So, that is why it is called a window comparator. It is sensitive to two threshold voltages of the input. When the lower threshold is crossed, the output changes state and remains in the state until you again cross the upper threshold by changing the input voltage. So, window comparators have got very nice applications, and we also saw another variation of a relaxation oscillator which you would have come across in transistors, the astable, bistable, multi vibrators, which are basically relaxation oscillators. Here using comparator, a regenerative comparator to be precise, how you can use an additional RC and make a relaxation oscillator out of it, so that you can get a square wave output from the operational amplifier. You can generate a square wave, and if you take the output across the capacitor, you might recall we also got a triangular wave. So, you can generate a square wave and a triangular wave. We also saw the how to derive the expression for the frequency or the period of such an oscillator. So, these are the things that we discussed in the last lecture. So, let us now move on to the next one, which is again an application of nonlinear application of the operational amplifier. But in this case it is a very interesting scheme where we are going to use a diode, normal diode, a p-n junction diode made of silicon, which is about 1 rupee in the market if you want to buy, and that is not an ideal device, as we all know. It is not an ideal device because if you look at the characteristics, you have about 0.7 volts, which is called the cut-in voltage. So, only when you cross 0.7 voltage at the input, the diode will get forward biased and you will get sufficient current through the diode. So, that cut-in voltage 0.7 volts is what you have to sacrifice when you are using diode in the normal rectifying action. So, this will normally, so for example, I have an AC signal. How do I measure the AC signal? If I want to measure an AC signal, the one way to do that is you can rectify the AC signal and give it to a normal galvanometer or a voltmeter as the case and measure the voltage. The rectified signal will either have half wave rectified signal or a full wave rectified signal. We know what will be the average output of a half wave rectified signal or a full wave rectified signal, and therefore, you know what magnitude of the voltage will be, average voltage will be read by the voltmeter. We can calibrate that voltmeter in terms of either the RMS or peak voltage or whatever. So, this is a normal procedure to measure AC voltages. If my AC voltages is very large, for example 10 volts or 20 volts, if I want to measure that, I can directly put a full wave or half wave rectifier and connect it to a normal voltmeter, DC voltmeter, and from the magnitude of the voltage I will be in a position to calibrate the meter in terms of either RMS or whatever. But unfortunately, when my input signal is about 1 volt or even less, then if I use a silicon diode, you know, to forward bias a silicon diode, you have to sacrifice about 0.7 volts, which is the cut-in voltage of the silicon diode. So, if I apply a signal with a peak voltage of 1 volt, after passing through the diode for rectification, you will be left with only about 0.3 volts or so. which is a very low voltage. If I say 0.7, if I say it in millivolts, it is 700 millivolts, which is a very large magnitude of the voltage, and you will get only 0.3 volts if it is 1 volt peak, and that is about 300 millivolts. So, you have lost more than 700 millivolt of your input voltage across the diode. This is a very undesirable scheme. So, how do I then detect very low level signals? How do I measure very low level signal? Of course, there is one option available for you, and that is you can use a good AC amplifier. You can use an AC amplifier and amplify the voltage to a larger value, so that 0.7 is very insignificant. When you amplify the 1 volt by 10 times, it becomes 10 volts. In 10 volts, 0.7 volts is not too much of a loss, and therefore, you can calibrate using that by the normal DC. So, you must have an amplifier, but the amplifiers can be very expensive or difficult to construct. Therefore, is there a way by which I can use the same diode, PN junction diode, and still rectify very low level signals which are less than 1 volt or whatever. So, the point is that it is indeed possible to make the normal diode, silicon diode, as an ideal diode. For that, all that you have to do is have an op amp, which is not very expensive. If you just use an additional op amp along with the diode, you can make the diode behave like an ideal diode. So, that is the whole idea behind this active diode circuit. Now, you can see on the screen, I will tell you what happens. When I have a op amp, the op amp has got an open loop gain of about 10 power 5, 100,000 as the open loop gain typically. So, if I have a 0.7 volts as the cut in voltage in the case of a normal silicon diode, then if I use an op amp, the cut in voltage will become, as you see on the screen, Vk, the cut in voltage for the closed loop will be equal to Vk divided by AOL, where AOL is the open loop gain of the operational amplifier. So, Vk is about 0.7 volts normally, and AOL is 10 power 5, and therefore, 0.7 by 10 power 5 is about 7 microvolts. So, you can see the cut in voltage becomes reduced from 0.7 volts to 7 microvolt, which is a very small value, and this is the greatest advantage that you get when I combine an operational amplifier with a normal diode to obtain an ideal diode configuration. Having said that, I will just show you a typical circuit. You can see in the screen a typical circuit which makes use of an operational amplifier, as you can see, and a diode. This diode in the simplest case is a normal silicon diode. So, this configuration, you can see the feedback loop from the negative input is connected at this point after the diode, and the diode comes at the output of the operational amplifier. This resistor RL is actually the load resistance, and so this is a non-inverting buffer type of thing except for the diode. So, when I give a sine wave input here, I must get a sine wave input here if the diode is not there, but because the diode is there, something else is going to happen. Let us see what is going to happen. So, now when the voltage increases from very low value, you find initially that diode can be in open condition, that means it is not forward biased. So, and therefore, there is no link, there is no feedback loop from this point to minus, because this is open. It is equivalent almost connecting to the ground this point. So, it is an open loop condition. So, when the voltage increases here, that this voltage will have to be amplified by the open loop gain of the operational amplifier, and we know the open loop gain of the operational amplifier is 10 power 5. So, whatever is the voltage here will be multiplied by 10 power 5, and that will be the voltage that will be appearing at the output terminal of the operational amplifier. And even if it is, let us say, about 100 microvolt, if the input voltage is just around 100 microvolt, I have to multiply by 10 power 5, and so you can get this will be about 1 volt or so at this point. So, you get 1 volt means you find the diode will be forward bias, because there is on this point at the output of the amplifier it is about 1 volt, and on the other side it is close to ground, and therefore this diode will become forward bias. So when the diode becomes forward bias, there is a closed loop here, and therefore as long as the output is going positive, the output here also, when the input is going positive, the output also is going positive, and it will be multiplied by 10 power 5, and therefore it will be a very large voltage, and therefore it will forward bias the diode. It will be much larger than 0.7 volts, and so it will be forward biased, and I will get the same voltage as it is changing. And when this will happen, whenever the diode cutting voltage is more than 0.7 volts. To become 0.7 volts here, I must have an input voltage which is 7.7 divided by 10 power 5, that is 7 microvolt. Therefore even when the input is beyond 7 microvolt, as it increases here, you would find the diode will be shorted, forward biased, and I will get the voltage here exactly in the same way as it is changing here at the input. So I will get all the voltages, anything above 7 microvolt I will get here at the output. Okay, what happens when the signal goes negative? When the signal goes negative, you can immediately see when the signal goes negative, the output will become negative, and therefore the output is open circuited. The diode is open circuit, it is no more forward biased. If it is not forward biased, the output will have to be the same voltage as this voltage here, ground, there is no current here, and therefore it will be 0. So you find all the negative excursion of the signal, the output will remain at 0. For all the positive excursion of the signal, the output will go positive. Anything beyond 7 microvolt, the output will go follow exactly the same as the input, and therefore what I will therefore be left with, if I look at the oscilloscope, will be a half wave rectified with the amplitude starting even from 7 microvolt. You will have no difficulty with reference to the cut-in voltage of the diode, which in normal case should be at 0.7 volts, but here because of the op amp, because of the open loop gain of the op amp, and because of the configuration, the way I have connected it, you find the cut-in voltage of the diode is reduced to 7 microvolt. So this is the greatest advantage of using the diode along with the op amp, so that even very low level signals, peak voltages, anything beyond 7 microvolt also can be rectified, and this output I can connect to a multimeter and then or a voltmeter and measure the average voltage. In this case it will be 0.31 times the peak Em by pi, the peak voltage by pi. So that will be about 0.318. If it is full wave rectified, it will become 2 Em by pi, so it will be twice that value. So that value I can now calibrate in terms of either the RMS or whatever that I want to do. So this is a very simple configuration using one op amp and a diode in the proper feedback scheme. Then you find I can get a off wave rectifier circuit using this combination. Once I have an off wave rectified signal, then I can have all application circuits of the diode that we have already discussed at the earlier lectures when I discussed about diode, semiconductor diode. So this circuit corresponds to a off wave rectified signal. I have explained here on the screen, when the input signal goes positive, the output goes positive also and turns on the diode, and the diode then acts like a voltage follower, and the positive off cycle appears across the load resistor. But when the input signal goes negative, the op amp output also goes negative and turns off the diode, because there is not enough voltage to forward bias the diode. Since the diode is reverse biased or open, no voltage appears across the load resistor, and the final output is almost a perfect half wave signal, because 7 microvolt is the only difference. Okay. Once we can get an ideal half wave rectifier, the question then is how to build a full wave rectifier. You know, we require always full wave rectifier when you want to amplify very small AC signal. When you want to convert it to DC, it will be nice to have a full wave rectifier. In the case of a normal full wave rectifier, you will use a transformer with a center tap, so that with reference to the center tap, the two ends of the transformer will be out of phase by 180 degrees, and therefore I can use two diodes to convert each half of the cycle, and therefore I can get a full wave rectifier signal. We have already discussed that. But when it comes to an operational amplifier applied ideal diode full wave rectifier, the scheme is slightly different. You cannot simply use that scheme, but there could be other clever schemes available, and one such clever scheme I want to discuss. So, you can see in the figure that I have shown on the screen, you have the circuit of a full wave rectifier and also the corresponding output waveform. So, the full wave rectifier, as you can see, both the half cycles should come in the same direction as it is seen on the bottom graph that you see. This is a full wave rectified output, and this is an input signal, which is going back and forth, both positive and negative excursions are available, and even the negative excursion is pushed on to the positive side in the output, and so you get a full wave rectified signal at the output. So, this is what you want to give as a signal, and this is what you want to obtain at the output. What is the circuit? The circuit is what I have here. You can immediately recognize, I hope, the first circuit here using the op amp is nothing but a half wave rectifier. I have used R1 RF here, which has got a finite gain when it is in the reverse biased condition. This diode is the one which we already seen, the one which is going to do the rectification, and I give the input signal which is in the form of a sinusoidal wave at this plane, and what I am going to get here will be a half wave rectified signal, as we have already discussed. Now, that is given to a second stage. In the second stage, you see what I have is a summing amplifier. I hope you can see that. This is one input V1 here at this point, and the other input is coming through this resistor here. So, this is input itself is coming as another input for the summing amplifier. The output of the half wave rectifier is given as one of the inputs. So, these two inputs are amplified by the summing amplifier, and the result is what you get here. So, the question arises, how do we get full wave rectifier when I have also sinusoidal input as the input here? So, I will try to explain to you with the signals that I have. Before that, perhaps I should tell you, for example, RF is 2R3, twice R3. The gain factor here for the rectified signal is 2. So, R3 for example can be 10K, RF can be 20K, and this R2 again here is 20K. That means the gain for the input AC signal is only 1, but the gain for the rectified signal is 2. This is the important point that you should remember. So, with this background, let us try to look at this various signals. You have a sinusoidal input, and the half wave rectified signal will be something like this. One half is cut off, the negative excursion, only the positive half cycles are there, and I still get peak, V peak as the peak of this rectified signal. Now, when I give it to the summing amplifier, the summing amplifier amplifies the signal to twice, I already said, and therefore it becomes 2 VIP. This signal becomes 2 VP as a peak voltage, and the other signal is the input signal which is coming to the summing amplifier, and for that the gain is 1, and therefore the same output is also there. So, these two signals will be added at the output, and what I get will be the sum of these two. So, if I add these two, what is going to happen? This is 2 V peak, this is V peak in the opposite direction. So, when I combine these two, I will get only 1 V peak in the upward direction. If I come to the second stage, in the second stage there is only one peak voltage in the upward direction, and there is nothing from the other input, and therefore when you sum them, you again get a peak voltage here in the same direction. So, like that for each wave you find you get only a net output peak voltage which is coming over here, and therefore when I monitor the output voltage of the summing amplifier, I get a full wave rectified signal. So, that is what is again shown here. This is a V in, this is immediately after the half wave rectification, and after I combine the two signals using a summing amplifier, I get the output, which is a full wave rectified signal. Of course, there is some important points that we should remember with reference to the full wave rectifier. This is a precision rectifier. It is called a precision rectifier because it can rectify without that cut in voltage cutting in any of your voltage from the signal. It is only now 7 microvolt, which is a very small value, and therefore the diodes behave almost like an ideal diode. The circuit is very common and is pretty much you find in many of the textbooks. Now, the most important point is in this you have to use the resistors that we have seen in the circuit, R1, R2, R3, RF, all those things will have to be very precise resistors with the tolerance 1% or even better. The tolerance of these resistors should be very good. We have to also worry about the high frequency response. The high frequency response of this circuit is not good when you use very large resistors. So, you have to, if you want to improve the high frequency response, you have to reduce the resistors that you make use of in the circuit, and also you should try to use a low impedance output from a signal source, the sinusoidal source. All these things we will also see, and you can have a precision rectifier having very good linearity even at the millivolts range. Okay, even a couple of millivolts at very low frequencies, you would find the full wave rectifier works very well without any great difficulty. So, having seen the two circuits now, we have seen one circuit which is a half wave rectifier signal, half wave rectifier, and the second circuit is a full wave rectifier which makes use of a summing amplifier and a normal half wave rectifier in combination. So, now I will move on to the demonstration lab table and show it to you that these two circuits, how they work one after another in the same manner in which I explained to you the working of these circuits. So, you can see the circuit board here. Okay. This is the same circuit which I explained to you. You have the V input here, and the negative feedback loop contains the diode, and you measure the output voltage after the diode, and there is a 10K resistor as the load resistor. This is a normal 741 op amp. The same circuit is wired here. You can see the op amp here, and you can see the normal silicon diode connected here, and this is a 10K resistor, the load resistor, and the VCC and etc. are all connected to the dual supply, and the wiring is completed. The input is given from a function generator, which you can see here. I can select the frequency here. I have now selected in the 100 hertz range. This is the one which is a depressed pin, and it is in sinusoidal mode. I can have sine, triangular, square and things like that. I am now in the sine mode, and I am in about 100 kilohertz range, and the frequency can be varied using these two knobs, and the output voltage can be varied in course 0.2 volts, 2 volts and 20 volts, and this could be for continuous variation. The output I have taken, there are two outputs here, one is 600 ohm, the other is 50 ohms. I have actually taken from the low impedance output, the 50 ohm output, and I have connected here. So, what I have connect at the input is a sinusoidal input around 100 hertz, and the output you can see I am monitoring using an oscilloscope. This is a dual trace oscilloscope. You have got two traces, and the two inputs are given from the input. The bottom one is actually the input signal connected to the circuit. The top one is the output signal. After rectification, you can see there is a half wave rectification achieved. You do not have any output here when the signal is going negative, and when the signal is going positive, you get that alone coming here. Now, I will vary the amplitude just to you can see here, and when I change that, the output amplitude also varies, and therefore, if I change the frequency, the output also changes. You can see that. Therefore, I am changing the frequency now, and correspondingly if you look at the oscilloscope, you find there again the frequency is changed. So, you can see it is a output corresponding to the circuit, and it is a half wave rectified signal. So, it is a very simple circuit. Again you can see just I have used only one op amp here and I have used one diode, that is all in the feedback loop, as very simple circuit which is able to perform output rectification even for very low signals. How do you know it is doing it for very low signals? You can see from the amplification factor in the oscilloscope, it is presently in about 0.2 volts per division, and so it is around 0.4. So, even for 0.4 I do get a very nice signal here, and that shows that even for very low level signals you will be in a position to have the half wave rectified signal. Now, I will show you the next circuit, which is a full wave rectifier signal. Now, I want you to observe the circuit here. It is the same as what I discussed. The first circuit is an ideal half wave rectifier, precision half wave rectifier, which we have already seen using an op amp and a diode, and the second circuit is actually a summing amplifier with one input coming from here, the other input coming from the input. So, these two are summed and that is what you get, and you know when you combine these two, what you get will be a full wave rectified signal. Now, the gain of signal for the half wave rectified signal is 2. This is 10k and this feedback resistor will be 20k in the actual circuit, and similarly this will be 20k and 20k, therefore, this gain is only 1. So, now what you see here is an op amp, first op amp, in which I have used the diode here. This diode is 4148, slightly different diode than what I have used, but this is again a silicon diode, and this is the second operational amplifier which is used as a summing amplifier. I have 20k in the feedback resistor, all of them are precision resistor, 1% resistor, and at the input again I have a 10k resistor here. So, the circuit is exactly same as what you see here, and I have now given the input from a function generator as before. You have the sine wave input and the frequency is around 1001 kilo, and therefore, I can measure the frequency and the amplitude over here, and now this input is given as the input for the circuit. The input is given here at the circuit, and the output is monitored, both the input and the output are monitored in the oscilloscope, as you can see on the oscilloscope. So, you can see the bottom one is the input signal and the top one is actually the output signal. The bottom one is a normal sinusoidal wave, which is the input I give, and at the output you find it is a full wave rectified signal. You can see both the halves are coming in the bottom, and if you want to have the other way, if you want to have the signal coming up to the positive side, all that you have to do is interchange the diodes that you have seen in the circuit. For example, these two diodes, if you invert this diode and this diode, if you change the direction orientation, then you will get the full wave rectified signal for the corresponding to the other side. So, you can do the full wave rectification easily by using one half wave rectifier and another summing amplifier. By properly choosing the gain, you will be in a position to get a full wave rectified output, as you have seen in the oscilloscope. If I vary the amplitude, as you can see on the oscilloscope, the output also changing here, and if you really measure the voltage, it is around again 0.2 or 0.4 volts, as you can see on the dial, and therefore, it is for very low signals that you get a full wave rectified output, and therefore, this is a precision full wave rectifier circuit. So, we have seen the demo corresponding to the two circuits. One is the precision half wave rectifier using operational amplifier, and the second one is a precision full wave rectifier, where we have used a half wave rectifier along with the summing amplifier to cleverly obtain full wave rectified signal. This is all discussed in many of the standard textbooks. Now, we will go further and try to see how to make an active peak detector. The peak detector is very useful whenever you want to measure AC signals. The one way to do that is you rectify the AC signal and connect it across a capacitor, so that the capacitor charges to the peak of the input signal, and if the time constant of the output is so chosen, the output will remain high or at the peak voltage for a longer period, so that you will be in a position to make a measurement using a normal DC voltmeter. So, how do we make a peak detector using operational amplifier? And it is a very simple thing. We have, you can see on the screen now, I have shown the circuit of an active peak detector using a precision diode here. The diode on the op amp is in the form of an ideal diode by having in the feedback network, and the output I connected to a capacitor along with the RL. So, if the time constant of the RLC is very large, then you would find the input signal will charge to the peak value the capacitor, and before it discharges the next peak voltage will come, etc., and therefore, it will almost remain at the peak voltage except for the small loss due to the RC time constant. So, here again you can do the peak detection for very low level signals less than 1 volt. You can comfortably convert them into peak voltage and then measure using normal multimeter or DC voltmeters. So, now I will perhaps show you the peak detector on the demonstration lab, I have a demonstrated board, and then I will come back and continue with the rest of the demonstration. Here you can see the same circuit, which is a peak detector. You have the precision rectifier here with the diode and the op amp, and you have a capacitor here connected for peak detection, and this is RL, the load resistor. The corresponding circuit is shown here. You can again see the operational amplifier, you can see the normal diode, and I have put about 100 microfarad capacitor in place of this, and I have RL, which is around 10K here. The input is again given from the function generator. As usual in the previous case, the output is connected to the input of the circuit, and the output of the circuit as well as the input of the circuit are monitored on the oscilloscope, which you see here. On the oscilloscope, this is the input, the sinusoidal wave at the bottom, and the output you see is a DC. It is a straight line, it is a DC. But how much is the DC you can measure by using the DC key here. If I press the AC and the DC key, now it is in DC and now it is here. If I now release that, if I make it into a ground, you can see the signal comes at this point. If I release it, it goes up. So, that much is the peak. Now, what I will do is I will bring it at the bottom or at the center, and then you can see it is actually going up to the peak value. So, when I put it into DC, it goes to the peak value. So, it has been charged to the peak value, and even if I increase the input amplitude by using the function generator, I am going to increase the amplitude. I am going to increase amplitude now, and you would find at the output in the signal in the oscilloscope, again you see a magnified signal, and if I again make it peak detect, you can see it is going up to the peak now, the corresponding peak now. So, it is indeed detecting the peak. So, instead of using a multimeter, I wanted to show you by using the DC coupling here that it goes from the 0 line to the peak value here, and this is the DC output that I get across the capacitor. This is the output. So, the output is a DC, therefore, it looks like a straight line, but it is shifted with reference to the 0 line up to the peak value, and therefore, it is indeed a peak detector. I hope you understand that point. So, a very simple op amp, diode and a capacitor, we are able to make a peak detector, and once I make a peak detector, I can connect it to a multimeter or whatever and calibrate it in terms of either RMS or peak voltage. So, we have seen the 3 different circuits so far. One is a basic precision diode or a rectifier, half wave rectifier, and then we also saw a full wave rectifier, how a half wave rectifier along with a summing amplifier can be constructed to give a full wave rectifier. We also saw a peak detector by using a capacitor at the output. So, once I have a diode, then I can have different type of application circuits with the diode and a capacitor. You know, we have already discussed it when we discussed about p-n junction diode. For example, active positive clipper. You already know of positive clipper or negative clipper or whatever, and the active positive clipper makes use of and precision diode. A diode which is along with an operation amplifier becomes an ideal diode that is used for generating the various clipping circuit and the clamping circuit, and that is what we are going to see now. So, let me show you a very simple circuit of a positive clipper, where again I have used an op amp and the diode. So, the diode and the op amp combined becomes a precision rectifier, and I give a AC signal here with a peak voltage Vp at the input, and at the output I should get a half wave rectified signal in principle. But then what happens, the second input or the non inverting input of the operational amplifier, now I have connected to a potentiometer, a variable resistor, this wiper of the potentiometer, and the other end is connected to plus, the one end is grounded, and therefore, when I move this wiper I can move it to this extreme, then it will become V plus, and when I move it to this extreme it becomes ground. So, I can vary this voltage at this terminal from anywhere between 0 to plus V could be any voltage, 2 volts or 4 volts or whatever. So, I can vary this voltage here and I can change the bias here. Now, when I change the bias, what is going to happen? If it is at the 0, this circuit is nothing but a simple half wave rectifier. So, you will find the signal, because this is now in this condition, when it goes negative, when the input is negative, you will find the output is also negative, and therefore, the diode will be conducting. So, there is a short, there is a feedback loop, and therefore, the output goes straight there, the output goes straight at the output terminals. But when the input goes positive with reference to the other terminal, then you find the output will become positive. At that stage the diode will be reverse biased. So, diode will not work, it will be open, and therefore, the output will remain equal to this voltage, and that voltage here is what you get at the other terminal, and therefore, you will find initially you should get a half wave rectified signal, but if I now maintain this terminal at some voltage different from 0, for example plus 2 volts, then till I get plus 2 volts, if anything more than plus 2 volts if I apply here, this voltage is more than this voltage, and therefore, I get a negative, then it is shorted, and therefore, the output goes straight there. If it is more than 2 volts, you find this is opened up and you get the corresponding signal, and so you find the output is clipped at this V reference 2 volts in this case. If I make it 2 volts, the positive peak will be cut off at 2 volts. If it is 1 volt, the positive peak will be cut off at 1 volt. So, depending upon where I put the reference, this output will correspondingly be clipped. So, the negative input will automatically come, because during that time there is a feedback and you get the exact output voltage coming over here with a unity gain buffer type of thing. So, you get a clipper with a positive points clipped at this place, depending upon what reference you have in the operational amplifier. Now, if you want a negative clipper, what do you do? All that you have to do is reverse this diode and reverse this reference voltage. So, you can do that and have the positive cycle completely, and the negative cycle can be clipped wherever you want. So, if I want, some cases you want both sides clipped. So, when I take a sine wave and clip both sides, I will get almost sort of a square wave. So, there is one such circuit which I wanted to show it to you. So, you can see here the circuit now shown has got 2 Zener diodes connected in opposition together, and therefore, the output will be clipped on both sides at the VZ, plus VZ and minus VZ. So, that is what you get, and actually when this one Zener diode is breakdown voltage, having breakdown voltage, the other Zener diode will be forward biased. Therefore, you will get about 0.7 volts in addition to VZ. That is what is shown here as VZ plus Vk, that Vk is again 0.7 volts, which is the cut in voltage of a diode. So, VZ plus Vk will be the point at which it will be clipped both on the positive side and the negative side, because one Zener breaks down for one orientation of the signal for one excursion of the signal, and the other Zener diode breaks down for the other excursion, and therefore, what you get will be a clipped sine wave or basically something close to a square wave. So, when you want to convert a sinusoidal signal into square wave, you can make use of a clipper of this type, which uses Zener diode in the feedback, and you can get a square wave. Now, I will show you a simple circuit, the same circuit implemented for a positive clipper. So, the circuit here is the same as what I just now discussed as an active positive clipper. So, you have an op amp, you have the diode, and you have this signal input here, you take the output, and on this side you have got a potentiometer. The wiper of the potentiometer is providing the reference voltage for the positive terminal or the non inverting terminal of the operational amplifier. This is a plus. I have used the power supply of the VCC plus VCC itself here, and that is what is being used for the reference voltage here. So, this is a circuit, and the corresponding circuit is shown here. You can see the diode, you can see the operational amplifier and the resistors, and the input is provided from the function generator. Once again, you can see the function generator here. So, you have again at 1 kilohertz the amplitude, and it is a sinusoidal wave, and the amplitude is adjusted using these two knobs, and this is given as the input in the board, and the output is connected to an oscilloscope. As a matter of fact, in the oscilloscope both the input and the output are shown simultaneously. If I slightly move, you can see the two signals. You can see that the bottom one is an input signal, the top one is a clipped signal. You can see the clipping there. The clipping can be modified by changing the wiper position or by changing the reference voltage here. That is done by changing the potentiometer here. So, when I change the potentiometer, I want you to observe the oscilloscope. I want you to observe the oscilloscope. So, you can see when I change the, you can see I am able to change the point at which the signal is clipped by moving the wiper. So, the reference voltage is what is being changed now, and thereby I am able to change the clipping voltage. So, you can see this is a positive clipper, and if I want a negative clipper, all that I have already mentioned to you, all that I have to do is change the direction of the diode and change the reference voltage on this side. Then you will be able to get a negative clipping, and you, as I mentioned to you, you can also do a square wave clipping, that is both sides clipping, dual clipper, both positive and negative, by using Zener diode or combination of such circuits. Having seen the clipper circuit, we also know a diode can also be used for clamping. That means DC restoration, as it is also called, whereby you can take a sinusoidal wave, normal sinusoidal wave. When you take the average of the sinusoidal wave, you will get a symmetric sine wave with reference to the baseline or the common line, the ground line. For example, on the screen you can see the example of a sine wave which is symmetric with reference to the ground, the common point. The excursions are equal on both sides, plus V peak and minus V peak for maximum values, and you can see it goes back and forth on both sides of the ground. Now, when I say I am clamping, what I actually do is I change this line with reference to the sine wave. I can take it all the way to the top, then I have clipped at the peak positive point and the entire voltage is only negative, or I can bring this line to the bottom and clip it at this point at the bottom, so that the entire voltage is positively clamped. It is clamped at this point, at the lower point, so the whole thing is positive. So, you can do either positive clamping or negative clamping, and the circuit is again very simple. You might recall, before I go to the actual circuit, because it is much easier to understand from our earlier discussion on positive clamping. Therefore, I have shown the earlier circuit also here for recapitulation. So, you can recall what we did earlier. You have used a diode here and I have used a capacitor, and I give a sine wave input at this point. Now, what I get will be a clamped sine wave. How this comes about I also explained to you in the previous case. When the input goes negative, then this diode can be forward biased. This is ground, this is going both positive and negative as the signal goes, and therefore, when it goes negative you find the diode is forward biased, and therefore, the diode will start conducting. When it starts conducting, it will charge the capacitor in the path to the full peak value. So, during one negative excursion of the input signal, the diode will start conducting and it will charge the capacitor to full peak value. Now, once that happens, when the input signal goes positive, the diode will become open circuit after the first cycle, and therefore, you can almost ignore the presence of the diode now. So, what is going to happen is you have now a new situation where the input signal is applied in series with something like a battery. The capacitor charged to the plus Vp and the diode open circuited acts like a normal DC battery of a value Vp. So, you have to now add this Vp to every instantaneous voltage of the input signal, and that is what you get as the output. So, when the input is maximum V peak, you have to add another V peak here due to the battery here or the capacitor, and so the total output will be 2 V peak, and when you go to 0 you will have this V peak, and when you go to the minus V peak, this plus V peak will add with that and you will get 0. So, the output will start going from 0 to 2 V peak as the amplitude, and therefore, what I have effectively done is I have clamped this 0 line at the bottom. So, it becomes fully positive and it is a positive clipper. So, the output signal has got 2 Vp as the maximum voltage. So, this is a normal diode capacitor based clamper. Now, for everywhere where I use a normal diode, I will still have the same problem of the cut in voltage, because this is 0.7 volts. When I want to clamp it using some 1 volt signals, it will all be lost, only 0.3 will be charging this, and therefore, the clamping will not be done very well. So, if I can make this into an ideal diode, then I can even use very low signals and get the clamping action completely done. So, therefore, I have used here an active diode, which is an op amp with the diode connected as in the previous example, and I have used the this. So, if you look at this as an ideal diode, this is my capacitor, the circuit is very similar to this, the RL is what I have at the output load resistor. So, this is the input signal. So, when I now give an input AC signal, you would find the clamper will charge for the first negative cycle. When it goes negative, this diode will become positive because there is an inversion, and therefore, the diode will start conducting even for about 7 microvolts, and therefore, the output will come completely and it will charge the capacitor. Once the capacitor is charged, this diode will become open circuited, and whatever input signal I give, it will be in series with this Vp, and the output therefore, will be shifted with reference to DC, average DC, by a value corresponding to Vp. So, the whole output signal will become clamped at the positive side. So, it will be 0 will be clamped at this point, and the entire excursion will be towards the top thing. So, the sine signal, the output has the same size and shape as the input signal, there is no difference except for the DC shift, only there is a additional DC shift which is provided due to the capacitor charging to the full value of the peak voltage. So, in this case, the output voltage is a sum of the input voltage and the capacitor voltage, as I already mentioned to you. V output is equal to V in plus V peak, and V in is a sinusoidal voltage with a peak voltage Vp. When I add it with this, so when this becomes plus Vp, the total becomes 2 Vp, when this becomes 0, the output is Vp, when it becomes minus Vp, the output is 0. So, the whole thing, there is nothing which goes below 0, even though the signal goes below 0, because you are adding with a Vp, the output becomes only all positive starting from 0 up to a maximum of 2 Vp. So, that is the active positive clamper that we wanted to discuss. Now, I will try to show you the demo of the active positive clamper, and then we will go further. Okay. Positive clamper vandirucha. Chinna break sir. So, this is the circuit of an active positive clamper, which just now I discussed. You have the input sine wave from an oscillator, and you have a capacitor here, and then you have the ideal diode with the operational amplifier and the diode. This is the load resistor, and you take the output at this point. The positive terminal is connected to ground, the inverting terminal, non-inverting terminal is connected to the ground. The same circuit is wired here. You can see the capacitor is here about 10 or 50 microfarad, and this is the diode that I have here, and this 10k resistor, and the wiring is done exactly in the same way. Now, the input is connected to a function generator as before. You can see here it is in sinusoidal mode, and it is at about 110 kilohertz or something, and the frequency and the output amplitude etc. can be changed using these knobs, and the output is connected to the input of this circuit, which is a active positive clamper. Both the input and the output waveforms are monitored using an oscilloscope here. The bottom one is the input signal, the top one is the output signal. Now, you do not see any difference here, both of them are identical. That means the gain of the amplifier of the circuit is 1, but there is a difference. What is the difference? That difference you can see by looking at the DC situation. So, for example, I have a knob here, which when I press, you can see this is now AC mode, this is DC mode, AC mode. So, you can see in the bottom sine wave, the AC is with reference to the ground, which is here. For the top one, you would find when I make it into DC, you find still the sine wave is there, and it is moved up to this line, the central line. So, that is what actually, now you see it is symmetric to the central line, it is symmetric to the central line, and when I DC couple it, you find it moves up to this. That means the entire output has moved with reference to this as the reference line or the 0 line. So, I have clamped it positive. So, I will show you again and again number of times, so that you can see on the screen that initially it is symmetric. Now, when I DC couple it, the whole sinusoidal voltage moves up, that means it is positively clamped. That is what we see here. Whereas, the same thing if I do for the lower signal, you can see that there is no DC there. There is no DC, therefore, when I put DC coupling, I get only a straight line. That means there is no DC, everything is only AC. Whereas, in the top one, you see all of them are AC, but with reference to a 0 line, which is at the bottom, and therefore, it is a varying DC, sinusoidally varying DC, all with reference to this reference point. Therefore, it is positively clamped, that is what we mean. So, this the way to identify the DC clamping here. Now, if I want a negative clamping, all that I have to do in the circuit is invert the diode here, and then you will get a negative clamping. That means the whole signal will move to the negative side. The clamping will be done with reference to 0, and the 2 peak will be on the negative side. Just as we saw now on the positive side, you can go to the negative clamping by just interchanging the diode, turning through 180 degrees. You can turn and then redraw the circuit, you will be able to get a negative clamping. The positive clamping and negative clamping are also very useful in different applications in electronics. So, what we have done today is to look at how a normal diode can be made into an ideal diode with the combination of an operational amplifier, and we also saw how different applications of an ideal diode can be used for half wave rectification, precision full wave rectification, and then peak detection using a simple capacitor, and then clipping circuit by giving some bias, and a clamping circuit. All these different circuits based on active diode circuit using an operational amplifier, how a precision rectifier can be constructed, and the application based on those diode circuits have been discussed. Thank you.